Hello everyone. In this Robot Operating System version 2 tutorial, or briefly ROS2 tutorial, we explain how to properly load and display URDF and Xacro model files in Gazebo. In particular, we explain how to Number 1. Write simple URDF and Xacro models. Number 2. Write a Gazebo world file for embedding the model in Gazebo 3D world. Number 3. Write Python launch files and ROS2 package that will properly set the ROS2 and Gazebo environments and that will load the model in Gazebo. In this tutorial, we present a minimum working example of loading the model files in Gazebo. Here is the final model in Gazebo. It's a simple cylinder. We deliberately stick to the simplest possible model and basic Gazebo and ROS2 configurations in order not to blur the main ideas with too many coding details. Even in this simplified form, the example covered in this tutorial might be challenging for complete beginners. However, we invested a significant amount of time and effort to present all the steps clearly. Also, we noticed that some students watching this channel expect that we will provide links to code files developed in this tutorial such that they can simply copy and paste the code. Well, this is not a good programming practice. By simply copy and pasting the code that someone else wrote for you, you will never understand and properly learn ROS2. The proper way of watching this tutorial is to listen to our explanations and to understand every step. You can simply pause the video and type the commands we are explaining in your terminal or in your Python editor. But before we start with explanations, we need to mention the following. It took us a significant amount of time, energy and planning to create this completely free video tutorial, as well as almost 500 free video tutorials that you can find on this YouTube channel. And consequently, we kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start with explanations. The first step is to double check that we have the correct combination of ROS2 and Linux distributions. This tutorial will work 100% correctly in ROS2 Irwini and in Linux Ubuntu 22.04. So let's verify that we have the proper Linux and ROS2 versions. To do that, let's open a terminal. And inside of this terminal, let's first verify our current Linux version. We can do that by typing this. And as you can see over here, on my machine I have Ubuntu and the version is 22.04. Next, let us double check the ROS version. To double check the ROS version, let's go back to the terminal and let's first source the environment. That is, let's execute this ROS2 setup file. Okay, after that, let's print our current ROS2 version. And as you can see over here, in my case, I have Iron, and Iron is an abbreviation for Iron Irwini. Perfect. Everything explained in this video tutorial will most likely work in other ROS2 distributions. However, instead of Iron abbreviation in Linux and ROS2 commands, you need to insert the correct abbreviation matching your ROS2 distribution. However, I strongly recommend you that you install ROS2 Iron Irwini. In fact, I created a separate video tutorial explaining how to properly install ROS2 Iron Irwini on a Linux Ubuntu machine. A link to that tutorial is given in the description below this video. The next step is to install the necessary packages. For that purpose, open a new terminal, and in this new terminal, you need to source this setup file. Remember, every time you want to develop a new ROS2 package or a program, you need to execute this setup file. This means that you need to source this file. Okay. Next, let us update the list of packages. We do that by typing sudo apt-get update. Enter your password. Okay. The next step is to install Geditor. Geditor is very powerful and, more importantly, simple to use editor for typing ROS2 code or for developing Python programs. As you can see over here, all the requirements are satisfied in my case. This is because I already installed Geditor before creating this video tutorial. However, in your case, you will see the installation progress. The next step is to install this ROS package called ROS Iron Joint State Publisher. We do it like this: sudo apt install and the name of the package. Here it is. All the requirements are satisfied. However, in your case, you will see the installation progress. The next step is to install this package. Sudo apt install and the name of the package is ROS Iron Joint State Publisher Graphics User Interface. And finally, we need to install our Xacro ROS package. So we type sudo apt install ROS Iron Xacro. Perfect. Next, we need to install Gazebo and its tools. To do that, we need to run this command. Sudo apt install ROS Iron Gazebo ROS packages. And after that, we need to install Gazebo tools. Okay. Now, it's a very good practice to verify the installation. To verify the installation, we will simply type Gazebo, and let's see what will happen. And here it is. Voila! Congratulations! Now you have Gazebo on your Linux machine. Next, close the Gazebo window, close the terminal, and let's create the workspace and our package. For that purpose, open a new terminal, and in that new terminal, source the environment. That is, source the setup.bash file. Next, let's create the workspace folders. With this Linux command, we are actually creating the folder called ws gazebo, and inside of that folder, we are creating another folder called source. This is a standard step. Over here, WS stands for workspace and Gazebo is the name of the workspace. You can also use some other name for the workspace folder. However, everywhere in the code you need to use that name. Next, we create and build the workspace. To do that, let's go to the root folder of our workspace and let's execute this command. This command will initialize, or better to say build, an empty workspace. Okay, the next step is to create the package. To create a package in ROS2, you always need to go to the source folder. In that folder, you need to execute this command. Let's analyze this command. ROS2, then package create, right? So we are executing ROS2, we are creating a package. This is the build type. We are using CMake, and this is the name of our package. The name of the package is Gazebo Test. Of course, you can name it differently. However, everywhere in my code, you will have to use your name. Consequently, I strongly suggest you to stick to this name. Now, let us navigate to our folder, but before we do that, let's not forget to execute this command. And as you can see over here, our package is created and it's an empty package. Next, let us navigate to this folder inside of our package and let's look into the content of this folder. This is the main folder for our package, and its absolute path is the workspace, source, and the name of the package. Inside of this folder, we will create two folders. We will create launch folder and the model folder. These two folders are very important for us. The launch folder, and let's see it, here it is. The launch folder will contain the Python launch file necessary to run the model in Gazebo. The model folder, on the other hand, will contain the Xacro and URDF source files of our model, as well as a Gazebo empty world file that is used in our environment. Note that URDF actually stands for Unified Robotics Description Format. This is a file format that is used to specify the geometry of robots and some other properties. On the other hand, Xacro is an XML macro language used to parameterize and simplify URDF model development. Next, let's now build the complete workspace once more. To build the workspace and packages, we need to navigate to the source folder. That is, we need to go over here. When I say source, I mean the source folder or root folder, to be more precise, of our workspace. So here it is, and inside of this folder we need to execute this command. And this will again build our package and our workspace. The next step is to create URDF, Xacro, and world source files. That is, we are creating our model files. For that purpose, we need to go to the folder inside of our package. That is, we need to go over here. We need to go to the model folder. And inside of that folder, we need to create a Xacro file. To do that, we will use gedit. So we type gedit and we specify the name of the file, robo.xacro. And here it is. Now, to make this video tutorial as short as possible, I will simply copy and paste the content of that file, and I will explain every line. My suggestion is to pause the video and to type line by line as I explain these lines. Okay, so let's start. Okay, let's start with explanations. This first line should not be changed. That is, every Xacro or URDF file starts with this line. Then, over here, this part is always the same for every URDF file except for this part. Over here, you need to specify the name of our robot or the name of our model. In my case, it's simple robot. This is how we write comments. Again, this is a comment. And these two lines are very important. Over here, we define the length and the radius of our cylinder. To do that, we use Xacro macros. We specify property, we specify name, and we specify the value. Now, later on in our code, instead of writing 0.5 everywhere, we will just type base link length if we want to denote the length. We can also perform algebraic operations of these macro variables. I will explain this in my future tutorials. We define the length, we define the radius. Again, this is a comment. Now, this line is also important, and this line will be actually explained after I explain this file. This line loads the file called robot.gazebo. We still didn't define this file, we will define it in the sequel. This file will contain additional properties that are necessary to properly load the URDF or Xacro files in Gazebo. To do that, we need to specify the path. Gazebo test is our package, model folder, and the name of the file. This file will be created later on, as I mentioned. The first link that we need to have is a dummy link. This link is actually an artificial link that's used to fix our model to the ground plane. This is how we start the link, and this is how we end the link. And this is the name of the link. Next, between the first and the second link is actually our cylinder, we need to have a joint. The name of the joint is the dummy joint. The type is fixed. This is very important since we want to fix the first link to our dummy link. We need to specify the parent link. The parent link of this joint is actually our dummy link. The child link is the next link in the kinematic chain. It's actually the base link, and we end the joint environment. So we start, end. Inside we specify parent and child, and that's a standard pattern. The next step is to define our cylinder. Here's how we do that. Here we start our link, and over here we end the link, line 53. And let's explain every line of our link. You can actually ignore comments. That is, these lines are comments lines, so you don't need to enter them. Start the link, we give the link name, base link. Over here we define the visual representation of the link. We start visual, we end visual. Over here we define the geometry of our link. The geometry is a cylinder. Here's the length. And look what's happening over here. The length is actually a parameter. It's the base link length. And if you go up, you will see that over here we define the base link length. So instead of writing 0.5, we just write the name of this variable and we use the $sign and this specific notation. Then we define the radius. Again, the radius is a macro variable, base link radius, and geometry is completed. You can skip these lines since they're comments. Next, we need to specify the origin, RPY. R is actually roll, P is pitch, and Y is yaw. These are the three rotation angles of the coordinate system of our link. Nothing should be changed here. The angle should be 0, 0, 0, and over here the translation of the coordinate system of our link with respect to its parent joint is 0, 0, 0. And that's the visual representation of our link. Next, we need to define these collision parameters. Namely, if we want to model the dynamics of our link, we need to model collisions, and Gazebo requires that. So over here, we kind of put our link inside of the collision box, which is actually not a box, it's actually again a cylinder, and we simply copy and paste the cylinder geometric representation. So length, radius, we end the geometry, and we specify the origin. Note that this part over here is actually identical to this part over here. Next, we need to define inertial properties of a link. Namely, since this is a rigid body, the dynamics is mainly defined by the moments of inertia. Not the mass only, but the moments of inertia. And over here, we specify the centers of the moment of inertia, we specify the mass, and we specify the values of the moments of inertia. Here you have 6 parameters, they actually define the tensor of inertia, and over here I entered arbitrary values. Since I'm not currently modeling a very realistic link, I'm just demonstrating the basic principles. So you can enter these values. And again, at the end, you need to end the link. So this link ends here, and it starts here. Actually, it starts here, correction. So it starts here, and it ends here. And at the end of your code, don't forget to close the robot environment. So see what's happening over here. Line 57, we end the robot environment, and let's see where we start the robot environment. We start the robot environment here. Now, a good check of your URDF file is the following. When you open some environment, or this notation, if you start link, you need to end the link. If you start joint, like this, now notice what happened over here. We're starting joint inline, you actually have to again end joint. This is very important to keep in mind. Again, here's the file, here's the first part of the file from 1 to 29, and let's see, the second part is from 29 all the way to 57, and that's it. Next, don't forget to save this file, and you can close the file. Next, let's go back to our terminal. The next step is to create another file. The name of that file is robo.gazebo. This is the gazebo file that is actually included in our original Xacro file. To do that, let's go to the terminal, and in the same model folder, type this. And again, I will simply copy and paste the gazebo portion of my Xacro file. Again, this line should not be changed. That is, keep it as it is. We start a robot environment, we end the robot environment, and over here we define something related to gazebo. We start gazebo, we end gazebo. And inside we have a plugin. We have some additional package called plugin that's used to run properly gazebo. The name of that plugin is Gazebo ROS Control. This is actually a plugin that will enable us to control our model from ROS. Here is the file name. This is the standard file name from this package. We didn't create this package, someone else created that package. And over here we specify the namespace. The namespace is actually the name of our robot. So this namespace should correspond to the name of the robot in the Xacro file. We end the plugin, we end gazebo. And over here we need to specify additional properties of our base link. These two parameters are friction parameters. They are not important for the time being. Over here we specify the color, and finally we end the gazebo portion of our base link, and we end robot, and that's it. Save this file, close this file, and let's continue with modeling. The next step is to create a gazebo world file. Namely, any model that we create should be embedded in some world. World can be, for example, bus station, can be a simple plane, can be a desk, can be, for example, some company floor or something like that. And we need to specify the world. Over here we will define a simple empty world, since we don't want to blur the main ideas of this tutorial with too many modeling details. Consequently, let's create a file called emptyworld.world. And again, let's simply copy and paste the content of the file that I previously wrote, and let's explain this file. Again, you can see the standard line, and over here you can see something new. SDF is actually a file format that's used by Gazebo. We start this file format and we end this file format. And as you can see over here, the commands, that is the environments, are pretty much similar to Xacro and to the other Gazebo file. We specify the name of the world and we end the world. Then we specify the light source, include, start include, end include, and over here we specify sun, nothing special. Now we need to define the ground plane. There is a typo over here. Include, start, and include, and we use simple ground plane. And that's it. For the time being, you don't need to understand more details about how to create worlds. As your knowledge of ROS progresses and as you learn more stuff, we will cover this topic and you will become pretty much familiar with how to create worlds in Gazebo and ROS2. Okay, so let's continue. Before we continue, don't forget to save and to close the file you just created. The next step is to create the Python launch file. The Python launch file is very important. It's used to create all the ROS2 nodes as well as all the Gazebo nodes and to combine them together. And we can just execute one launch file and Gazebo will start together with our model and together with all the nodes. To create our launch file, we need to go to the launch folder. Go to the terminal and go to the launch folder. Inside of that folder, create the launch file. The name of the file is gazebo _ model.launch.py. Notice here the extension py. Py is the extension of Python files. And again, to save time, I will simply copy and paste the launch file. And I will explain this file line by line. Over here, we import the necessary libraries. Then we import Node, which is very important, and we import Xacro. Notice that we already installed the Xacro package. This file basically consists of a single function. the name of this function is generate launch description, and this function will actually return this object called launch description object that will define all the nodes together with all the properties that will be used to start Gazebo. Next, we need to define a few things. First of all, here we specify the name of our robot, and notice that the name of the robot should match the name of the robot in the Xacro file. Next, this is the name of our package, and we will be using it quite often in this file. Next, we need to define a relative path to the Xacro file defining the model. Our Xacro file is inside of the model folder, and the name of the Xacro file is robot.xacro. Now, this is a relative path over here to the Gazebo world file. The Gazebo world file is in the folder model, and the name of the file is emptyworld.world. Here is the absolute path to our model. What do we do over here? This function, we will actually search for the path corresponding to our package, and name package is actually defined over here. So it will give us this. This will be the path, the absolute path to our package, and on top of that, we add model file relative path to define the absolute path to our URDF, or better to say Xacro model, that is to this file. Notice over here that we are using this function os.path.join. This function will actually join two strings. It will join the string matching the absolute path of our package and this string over here matching the relative path of our file. Similarly, we define the absolute path to the world model. Again, we get the absolute path of our package, and on top of that, we add this path over here. Now, this line is also very important. This line is used to get the robot description from the Xacro model file. We call Xacro.processFile function, we specify path model file, and here you should be very careful and connect this thing with this thing over here. So we are specifying the absolute path to our model file, that is to Xacro file, and over here we convert to XML. Next, I need to explain these two lines. However, there is an issue over here. As you can observe over here, Geditor is not properly aligning all the lines inside of this function. Namely, these two lines should be aligned such that they're inside of this function. In fact, in reality they are. However, for some reason, Geditor is not displaying them correctly. To avoid confusion, I will open this file from another editor. I will actually use Spider Editor. I like Spider Editor a lot, and to run the Spider Editor, I first need to run Anaconda. I need to run the Anaconda Navigator. You don't need to do this, as I mentioned. However, I strongly suggest you to actually install Anaconda Navigator. In fact, I created a tutorial that explains how to install Anaconda Navigator. And I will run Spider. Spider is a very powerful editor. Next, I will need to locate the files. So I will open the file. They are actually in my home folder. Here it is. Now source, Gazebo test, and here they are. Actually, they're not here. They're actually in the launch folder. Here's the file. Okay, now you can see the lines more clearly. These two lines actually correspond to these two lines in my Geditor. So I will explain them from my Spider environment. This line is used to define an object that actually contains information about Gazebo ROS package launch file. Gazebo ROS is not the package we actually wrote, it's the package that we installed. So what's happening over here? We are actually defining the path of this file, the absolute path. First of all, over here with the get package shared directory, we search for Gazebo ROS package, and what will happen behind the scene, this function will actually find the location of this package and where it's installed on our Linux machine. Then this is the name of the folder, launch, and inside of this folder there is a file called gazebo.launch.py. This is a file that someone else wrote for us. Now, what will happen behind the scene? When we execute our file gazebo model launch, we will actually execute this file implicitly, and then this file will in fact create all the nodes that we will define in the SQL, and we will actually also execute this file. We will explain everything in the SQL. Next, over here, we define the launch description. We add this object over here, and we specify the launch arguments. The launch arguments are also very important. We need to specify the world. We need to specify the absolute path to the world file, and here it is. This is actually the path to this file over here, and we can see over here that it's actually a dictionary. This is a standard notation. Okay, so let's go back to our G editor and let's continue with the explanation of the remaining code lines. We explain these two lines, and let's continue. Over here, we create a Gazebo ROS node and we define its properties. To do that, we use the function node. It's imported over here. Then we specify the name of the package. Again, this is the package that someone else wrote for us. Then we specify the executable file. This is the name of the file, the Python file that actually will create the node. And we specify the arguments. We specify the topic, and the topic is Robo description. And this Robo description actually should match the Robo description in our next node that I will explain in the SQL. And here we need to specify the entity parameter, and the entity parameter should actually match the robot Xacro name. The robot Xacro name is given over here, and that's the name of the robot in the Xacro file. And the output should be screen. That is, we want to display our model on the screen. The next node that we need to define is the robot state publisher node. Again, we use the function node. We specify the package. The package is robot state publisher. The executable file is robot state publisher. The output should be screen, and the parameters are very important. The parameters, you see this parameter, robot description. It's actually the robot description, and keep in mind that the robot description is actually defined over here. Over here, we actually created a complete robot description from the URDF, or better to say, from the Xacro file. And over here, we need to specify use sim time true. This is always the case when you need to run a node in ROS2. And here are the 4 or 5 final steps. Here we need to create an empty launch description object. So we initialize this object and we call it launch description object. And we need to add all the objects that we previously defined. First of all, we need to add Gazebo launch. So where is Gazebo launch? Here it is. Okay, the next thing that we need to add is this object. We define it over here. This is actually our Gazebo ROS node. And then we need to add another object, or add action, and we need to add our robot state publisher. After that, we return the complete object. And that's it. Simple as that, or not so simple. In fact, it's very simple once you write several of these files, and you can use actually this file as a template to create other files. Next, don't forget to save this file and close the editor. Next, we need to make a few important adjustments and to run the model. Next, we need to add the dependencies. To add the dependencies, we need to go to this folder. This is actually the root folder of our package, and we need to edit this file. To edit this file, we will simply type gedit package.xml. Here it is. Over here, we need to add several lines. We actually need to tell to ROS2 and to our compiler that we will be using specific packages. So let's do that. What are the packages that we need? Here they are. We need joint state publisher. If you keep in mind and if you remember that we actually used joint state publisher node in our launch file, then we need robot state publisher. Actually, I should correct myself. We defined this node. However, I also included this node just as a precaution. Then we need Gazebo ROS, since we are using the Gazebo ROS package and we're using the Xacro package. Okay, save this file, close the editor, and let's continue. The next step is to adjust the CMakeList file. CMakeList file is very important since it defines the main parameters when we are building the package and workspace. To do that, we need to go to this folder. We are actually in this folder, however, let's just go again once more to that folder, and let's edit our CMakeList file. Here it is. Now, before this line, if build testing, we need to add several lines. We need to add the following. Over here, we are informing our compiler and our CMake system that we have two additional folders that are important. We defined, or better to say, we made launch folder and we created the model folder. And now with this command, CMake will know that important files are over here. Okay, so let's save this file. Okay, next we need to perform one final build of the workspace and the package. To do that, let's go to the root folder of our workspace and let's run colcon build. And let's hope that everything will go smoothly. Perfect. Okay. The next step is actually to source the package. Note at the beginning of this tutorial, we actually sourced the bash file. We sourced the setup.bash file. However, as you can see at the beginning of this tutorial, the source or better to say setup.bash file is located over here. That is, it's located in the installation folder of ROS. However, now we need to source an additional file. Every package contains an additional setup file and it's located over here. By sourcing this file, we are actually creating an overlay. We are overlaying this setup file of our package over the setup file of ROS. And this is very important to keep in mind. So let's do that. Finally, we are ready to launch our model. To launch our model, we need to type the following. We type ROS2 launch gazebo test gazebo model.launch.py. We are basically executing the launch file that we previously defined. And let's press enter and let's hope that everything will work as expected. Here it is. Congratulations. This is our model. It's a simple cylinder. Now, it's always a good practice to keep an eye what's written over here and to search for errors or warnings. So let's see. You can see a very useful information over here. Process started with this PID, so we actually executed this file, and this file is actually a ROS control file, or Gazebo ROS file, better to say. We are running the robot state publisher, and you can see other important things. Okay, that would be all for today. I hope that you liked this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.